Hey, it's Neil Smith here. Hope you're doing well. The following problem seems a bit overwhelming, but be patient with yourself. It's just adding, subtracting, looking some numbers up in tables, throw in a few nuances, a couple concepts to keep straight, and before you know it, you'll be doing these problems. They're not that bad. You got this. Determination of compass error by azimuth of the sun, practice problem 4. Let's get this one going. All right, that's a good start. Okay, let's get all of our givens right here. So we have April 17th. They gave us the date. The date is April 17th, and these all take place 1981. And the zone time, 1516. Zone time equals 1516. DR position right here. So our DR position equals latitude 27 degrees 24.0 minutes north. Longitude is equal to 115 degrees 24.0 minutes east. And at that time, you observed the sun bearing 247. The sun bearing equals 247 degrees. The chronometer reads 7:16:26. It's the chron time. Is equal to 7 hours, 16 minutes, 26 seconds. And the chron error is equal to, chron error is 0 minutes 32 slow. 0 minutes 32 seconds slow. That means we add. If it's slow, we add. And now variation is given. Variation equals 4.5 degrees east, and it wants to know what's the deviation. Deviation. That is the question. What is the deviation? First step, we'll get our approximate GMT. Make sure we're in the right day. Our approximate GMT. So to find this, we take our zone time. So our zone time is equal to 1516. And now we have to figure out the hour correction to get to Greenwich. So take our longitude, which is equal to 115 degrees east, and divide it by 15. You don't have to worry about the minutes much here. If it was really close, like you were really close to 0.5 or whatever, you could use them, but just 115 divided by 15 equals 7.66. So that rounds up to 8. We need to get to the whole number. So 7.7 rounds up to 8. So 7.6 repeating, we round that up to 8 hours. And now is it plus or minus? See this east here? Let's just draw a little diagram to help us understand. This is Greenwich. It's the prime meridian. If you draw in the time zones, when you go east, you add. And when you go west, you subtract. So if you are in the east and you need to get back to Greenwich, you need to subtract. So we're going to subtract 8 hours. So minus 0, 8 hours. 6, 1, 15 minus 8 is 7. 7:16. This is our approximate GMT, right? So let's try to get our actual GMT. It's based on the cron time. So our cron time is 7:16. I'm just going to write this. Cron time equals 7 hours, 16 minutes, and 26 seconds. And the error, the cron error, is equal to 0 minutes 32. Do we add or subtract those? Well, this is slow, so we add it. So 26, 6 plus 2 is 8. That's 5, 58, 16, 7 hours, 16 minutes, 58. So that's pretty close. 7:16 we calculated. There's a possibility it was 12 hours ahead. But that's not us. We are right here. And this is happening April 17th, 1981. That's our GMT. Let's do over here. GMT equals. Good. Now with our GMT, we can find the Greenwich hour angle, or GHA, of the sun. GHA, and we start out for 7 hours, and then we do the increments. So the GHA for the increments, 16:58. 16 minutes, 58 seconds. So those are going to equal something. And then when we find those, we'll find the declination at the same time, because the declination is going to be just right next to it. And so is the D correction. So we'll set ourselves up there. Now we can jump into the Nautical Almanac and find April 17th. Hey, look at that. We're already there. See, you can flip through this book. You'll notice all of the months and days. So here we are, April 17th. The sun column, GMT. Here's the day 17. Hours, we're looking for 7. Here we are, 285 degrees, 5.9 minutes. 285, 5.9 minutes. 285 and 5.9 degrees minutes. And now you'll notice the declination's right next to it. So we're at 7 hours, right? April 17th, it's 7 hours. See this north? North 1028.1. North 1028.1. North 1028.1 degrees minutes. Now let's get our D correction. So our D correction down here is D is 0.9. You can see it right there. We need to know whether to add it or subtract it. How do we figure that out? Well, we come to our declination up here, which was north 1028.1. Now, if you go down to the next hour, is it increasing or decreasing? It's increasing as we go down. So we're going to add this. So it's a plus 0.9. And now when we go into the increments table to get this, our D corrections also in increments. The table is called increments and corrections. So let's jump back there and get these. It's in the back of the Nautical Almanac. Increments and corrections. We need 16 minutes. Here's the minutes over here. 11, we jump past it. 15 and 16. So 16 minutes, 58 seconds. We're way down here. Boom. 16 minutes, sun. So here we are. 4:14.5. 4:14.5. So we're at 4 and 14.5. We'll add those up. And now we'll get this D correction. Here's the D corrections. And for 0.9, there's 0.9 as our D value. And here's the correction, 0.2. 0.2. And we are going to add these, as we know. So 1.2 is 1 plus 2 is 3. 8 and 0, 8, 28. So this is north 10 degrees, 28.3. That's our declination. And now let's add these together. 9 and 5 is 14. 6, that's 10. And 1 here. Okay, yeah, 20.4 minutes. Good. Just double checking. All right. 5 and 4 is 9. And there's 8. 289. And then 20.4 minutes. This is the GHA of the sun. Greenwich hour angle of the sun. And now what we need to do is we add east longitude. So we add our east longitude. See, again, over here, we're to the east of the prime meridian, which is Greenwich Mean Time, which was the GHA, the Greenwich hour angle. To the east, we add. So we add our east longitude, which is 115 and 24.0 minutes. 24.0 minutes. So we're adding our east longitude to get our LHA. 4 and 0 is 4. 0 and 4 is 4. 2 and 2 is 4. 9 plus 5 is 14. 1. And that's 1. That's 9. 10. Carry the 1. 3. So that's 404. 44.4. And this is our LHA, but you'll notice we're not going to find 404 in the book. So that's LHA of the sun. That's local hour angle of the sun. So we need to get this to where we can find it in the book. If we subtract 360, we went all the way around and kept going. So you subtract 360 and we'll get something that we can find in the table. 404 minus 360 equals 44. Why not? Let's keep going with the fours. 44.4. Okay, so this is the LHA, local hour angle. Local hour angle of the sun. LHA, the sun, is equal to 44 degrees, 44.4 minutes. Okay, so now with this information, we come up here and we can tabulate some stuff. So we're going to start off declination. Declination, and then we're going to need our dr lat, and then the LHA of the sun. So our declination, we calculated here, is north 10, 28.3, 28.3. And then our dr lat is 27.24, 27 degrees, 24.4 0.0 north. It's important. And then LHA, 44 degrees, 44.4 minutes. Okay. So let's see. How are we with these? We have to figure out if the DR lat and the dec, are they named the same? Yes, north and north. So they are the same. So we got dec and DR lat are same. Good. They'd be contrary. If one of these was south and one was north, they'd be contrary. So now with that, we can get our base argument. Our base argument, which is just the degrees. 10, 27, 44. 10, 27, 44. These are all the degrees. And now we can get our base angle or base Z from the site reduction tables. Site reduction tables. Here we are. Now, look at that. Looks like I opened to the page, one page off. If you flip through this table, you can see all the LHAs over here. There's two of them, one for each side of the planet. And then you have your latitudes here. They only go from 23 to 30. But in the other side of the book, you'll find all of these again, but lower latitudes. Okay, so we are, let's find this LHA 44. LHA 42, 43, 44. And we have to be the same. See, there's the same page and a contrary page. We are the same because our declination and our DR latitude are both north. So we're the same, and we are 44, and we're looking for same 44, latitude 24, 10. Boom. So same 44, 24, 10. Same 44, 24, 10. 100.7. 27. Ha, I caught it. I knew something wasn't right. Same 44, 27. See that? 27. 10, 27, 44. So it's the same 44, 27, 10. We got the same 44, 27, 10. So we're at 103.7 is our base argument. 103.7. And that just carries down through all of these. Now we need to get our tabulated Z. This is interesting. You just take your base and knock each one up by 1. So this would be 11, 27, 44. And then it's 10, 28, 44. And then it's 10, 27, 45. And we write the answers out here. So tabulated Z. Take your time for this part. This is this is where I personally have been known to mess up. So tabulated. So now we go 11. So everything's the same, right? Same 44, 27, and now 11. Just slide it down one, right? 11. 102.5. 102.5. And now we get this to 28. Make sure you slide this back up. Here's a place you can mess up. Slide it back up to 10. And now your same 44, 28, 10, 104.7. 104.7. And now we need to get this LHA to 45. So there we go. Here's 10. So now we're same 45, 27, 10. So 27Z, 103.1. 103.1. Okay, base, tab. And now we need to find what comes next. Tabulated Z, the difference. The difference in the angle, or the Z. So you can see it's going down. This one's going up. This one's going down. Now we just find the difference between them by subtracting them. So 102.5 minus 103.7 equals minus 1.2. 1.2. Now 104.7 minus 103.7 equals 1. And 103.1 minus 103.7 equals minus 0.6. And notice right here, I have an addition sign. This should be subtraction. If you punch this number into your calculator and minus this, you'll come out with the proper sign if it's negative or positive. Good, so we got these. And now we go on to find the increments. So the increments are just these. These are the increments, the minutes. 28.3, 28.3 minutes, 24.0 minutes, and 44.4 minutes. These are the increments. And now we find the correction. And the correction is equal to the difference times the increments divided by 60. Let's do these. Okay. Let's put it over here. So, difference. So, negative 1.2 times 28.3 equals divided by 60 equals negative 0.57 minus 0.57. And this one, 1 times 24 equals divided by 60 equals 0.4. 0.4. And negative 0.6 times 44.4 equals divided by 60 equals minus 0.44. This total correction equals minus 0.57 plus 0.4 minus 0.44 equals minus 0.6. Minus 0.6. Okay, so now we take our base angle, which equals 103.7, and we put our correction on there, which in this case is negative. So we subtract 0.6. and we get our Z, which is going to be in quadrantal notation. So 0.1, 3 minus 0, 3. We get 103.1. And we need to name this. So it needs a north and either a north-south, over here east-west. We name it the same as our DR lat up front. North. And now, because LHA is less than 180, we name it west. So let's figure this out. Let's just draw it out. Here we go. So north, south, east, west. So we're north. So we're north this way, and then we're west. So we're going over here 103.1 degrees. So we end up somewhere down here. So this is our Z. But we need to find our angle from north, or ZN. So all the way around this way, this is our ZN. So basically, we can take 360 degrees minus this Z, and we will get our ZN. So Zn is equal to 360 minus Z is equal to 360 minus 103.1 equals 256.9. 256.9 degrees. That's our Zn. And now let's correct the compass. TVMDC. True variation magnetic deviation compass. When we're going down, we'll add west. We'll do the opposite to east. So our true is 256.9. 256.9. Our variation was given 4.5 east. 4.5 east. We're going down, we subtract them. 256.9 minus 4.5 equals 252.4. 252.4. And our compass was given, the sun is bearing 247. 247 degrees PSC. This PSC tells you it's in compass. And now from 252 to 247, it's less, so we know it's east. And now 252.4 minus 247 equals 5.4 east. 5.4 east. That's what we were coming here for. 5.4 east. Let's check the problem. And there we are, B. 5.4 east. And that is the answer to practice problem 4.